The resonant attachment of electron to form temporary negative ion and its subsequent decay through dissociation into a negative ion and one or more neutral fragments is known as dissociative electron attachment, in short DEA. The quantum coherence induced by attachment of a single electron from an incoherent electron beam has been demonstrated experimentally, which potentially opens up a new avenue of chemical control using low energy electrons. This quantum coherence is observed in the form of forward-backward asymmetry in the differential cross-section of DA to homonuclear diatomic molecule H2 about the direction of propagation of the attached free electron. So here it is the experimental setup schematics. This is the ion yield curve for H minus from H2, and here it is the velocity slice images of H minus from H2 and D minus from D2. The top panel is for H minus from H2 and the bottom panel is for D minus from D2. So here the forward backward asymmetry seen in H minus from H2. So here you can see that this is the electron beam direction top to bottom. So here it is clear that the ion intensity in the backward direction is more in comparison to the forward direction, and this asymmetry increases with increase in the incident electron energy for H minus from H2. This observation is understood in terms of the formation of a coherent superposition of two resonances of opposite parity on electron attachment. These two resonances dissociate to the same dissociation channel, resulting in interference between the two quantum paths coherently followed by the system. Now comes to the velocity slice images of D minus from D2. So here for 14 eV incident electron energy, the forward ion intensity is more in comparison to backward ion intensity, and with increase in the incident electron energy, this trend is changing. That means at 14.5 eV, the forward and backward is more or like same, and for this 15 eV, the backward intensity is more in comparison to the forward ion intensity. What is the reason behind it? The reason is the DA process competes with auto attachment of the electron from the negative ion resonance and the exponential dependence of the survivability of the parent anion against auto-detachment as a function of dissociation time. This fact reflects in the quantum coherence induced symmetry breaking in terms of the varying amplitudes of the interfering paths that depend on the width of the states participating and the dissociation time. Moreover, the relative phases of the two quantum paths would also differ for different isotopologues, resulting in the different amount of forward-backward asymmetry and its variation with attaching electron energy. The variation of the forward-backward asymmetry observed in D2 as compared to S2 has been understood to be the consequence of the isotope effect. The data shown here is the measurement done by me, though it is already reported in reference 3. The main motivation is to repeat the measurement for H2 and D2 around 14 eV resonance, is to reproduce the result such that the experiment is consistent with the previous reportings. As expected, we found exactly the same behavior for the angular distribution of the anionic fragments for DA to S2 and D2 as reference 3. Now comes to SD, which is another isotopologues of S2 but heteronuclear. Now the question is what will happen to the heteronuclear isotopologues, as both the ionic fragments H minus and D minus can result from the dissociation of the parent molecule SD minus but having slightly different dissociation limit. Will this result in isotope effect in differential cross section? Now let us see the results of our measurement on an angular distribution of anionic fragments for DA to SD. So here this is the velocity slice images of H minus and D minus from SD. The electron beam direction is from top to bottom. The top panel is for H minus and bottom panel is for D minus. As we can see here, the backward ion intensity is more in comparison to forward ion intensity, and this asymmetry increases with energy, and the images of D minus from SD also show the asymmetry and the extent of which is same as that in H minus from SD. In both cases, the backward ion injection is more favored over forward ejection. The momentum images of both H minus and D minus have same size, which is due to conservation of linear momentum, but the structure is more prominent in H minus than D minus due to the unequal energy partitioning among the fragments. Although the observed forward backward asymmetry in DA is due to the interference between the two quantum paths of opposite inversion symmetry, but no such inversion symmetry is expected to exist in SD, as the two atoms have different mass, making the center of mass of the system differing from the geometric center of the system. Now the question is, for 14 eV resonance in H2 and D2, we have to invoke the quantum interference between two resonance paths of DA to explain the inversion symmetry breaking. What would be the case with HD? We observe identical angular distribution and cross section for both the channels. How do we understand this for the heteronuclear diatom picture? Now I have two arguments which are completely opposite of each other. First one, SD behaves like a homonuclear diatom. Here the inversion symmetry can be explained on the same line as that of S2 and D2 with the reduced mass of the molecule as 1.5 AMU. The difference in the two dissociation limit H plus D minus and D plus H minus is about 3 millielectron volt. This is too small as compared to the uncertainty in the incoming electron energy. The identical angular distribution can be understood as the 3 millielectron volt difference in the dissociation limit is negligible as compared to the incoming electron energy, and hence the two dissociation channels H minus and D minus are identical, and hence they show identical asymmetry, angular distribution and cross section. This is a little crude argument. This is equivalent to saying that the small permanent dipole moment doesn't have any effect on the incoming electron attachment. If we consider the molecule SD as a heteronuclear one, both the resonances are doublet sigma plus resonance, which are the linear combination of G and U state, G plus U and G minus U, and will allow both S and P wave capture. The relative phase between the two partial waves may also be identical due to overlapping potential energy curves in the Planck region. But the catch is that how do they overlap if they have the same symmetry? But if we ignore this point, as the two states evolve with time, the relative phase would vary according to their potential energy curves. If the upper curve leads to the upper limit and the lower curve leads to the lower limit, they will show identical angular distribution. This is because the two paths are not interfering, and the single state based DA has characteristics of the capture, phase, amplitude of the individual partial waves, which are identical due to overlapping potential energy curves in the Planck region. If the two curves run very close to each other, then their solar probability will also be almost the same, since their corresponding dissociation times would be close to each other. A small energy difference between the two dissociation limit will have some effect on the relative cross section, but it can be within experimental uncertainties. To conclude, we have shown that the quantum coherence induced by single electron attachment in a homonuclear diatomic molecule S2 and D2 that results in inversion symmetry breaking causes similar forward backward asymmetry in both H minus and D minus channel from its heteronuclear isotope SD. The H minus and D minus channels not only show identical angular distribution with the same forward backward asymmetry, but also have equal DA cross section. These results indicate a dire need for reliable calculation using modern theoretical tools for determining the anion resonances and the lifetimes for a simple system of H2 and its isotopologues.